Ooh. Okay. Part 1 versus Part 2. We did Part 1, but let's review what Part 1 was. Part 1 of the fundamental theorem of calculus says an integral that goes from a to b of the function f of x dx, in parentheses, converts into the notation of the antiderivative f of x plus c on a to b, which converts to f of b plugged in first plus c minus f of a plus c. All right, we learned that last week. That is the fundamental theorem of calculus, part 1. We're now ready to move on to part 2. Okay, here's part 2. Okay, f of x dx. What if the bounds are not numbers? What if the bounds are other variables, like u and v? All right, what if the bounds are not numerical bounds? What if they are other letters? Okay, that does not stop you from doing the same process. All right, the same process would result in capital F with v plugged in, even though it's a variable, minus capital F with u plugged in, even though it's a variable. But what we want to be able to do to that is to be able to take the derivative again. And so you need to take the derivative of both sides because you're working with a variable instead of a constant. And this is how you write that. You use Leibniz's notation. I would like to take the derivative of both sides. I'd like to take the derivative of this side and I would like to take the derivative of the other side. All right, and let's see what happens if we follow our rules for derivatives that we've worked on all year. Okay, what will that be equal to? All right, well, let's take the derivative of each piece. This is just an addition and subtraction problem, so we can take the derivative of each piece. How do I take the derivative of capital F of v? Remember that v is a variable. What do I do? What's the derivative of capital F? Little f, right? The derivative of capital F is little f. What do I do with the v? What kind of? Almost. We take the derivative of the outside, and what do we do with the inside? Well, we leave it alone. And then we do the derivative of the inside, because the inside is a variable. So that's the rule, our rule that we learned. Okay, so we take the derivative of the outside, which is f. We leave the inside alone. And then we tack on the derivative of the chain rule, for the chain rule, which would be dv dx. All right, so first one's done. What's the derivative of c? C is a constant. Is c a number? So the derivative of it is 0. All right, so we'll skip ahead. Minus, now we take the derivative capital F of u. So the derivative of capital F is lower f, leave the inside alone, and then the chain rule would be du dx. And I'm just going to copy the other side the way it was. Okay, so here is the summary of what we have. The derivative of an integral. Okay? Opposites attract, right? The opposites meet. We have something doing a derivative and we have something doing an integral at the same time. The result is f itself with v plugged in times the chain rule on v minus f of u with u plugged in times the chain rule of u. That's how you work with functions that have a variable for their bounds. Okay, this is part 2 of the fundamental theorem of calculus. That's the summary, this part of it. All right, so let's practice. Differentiate both sides. So pretty soon in this chapter we're going to be doing both. Differentiate both sides, integrate both sides. We'll be doing it all. We got to go forwards, we got to be able to go backwards. All right, so here's example A. Y equals the integral where the lower bound is 2 but the upper bound is 2x cubed. So it's a variable. The function is the sine of t dt. All right, we would like to differentiate both sides. So the differentiate is just dy dx. That's the easy side. On the second side, we need the fundamental calculus part 2, which says when you're going to do something that has an integral with some bounds in it, then you start with the function itself, regular f. I don't have to change this into a capital F. I keep it, okay, look back at the thing, it's lowercase f, which is the same thing as what's on the other side in the integral. It's the same function. All right, so I need lowercase sine, regular sine, of what? Of the v part, which is the top bound, so 2x to the third, times the chain rule of what that 2x to the third is, which is times what? 6x squared, okay, minus, same function again, sine, with the lower bound plugged in this time, which happened to be 2, times the chain rule of that lower bound, which happens to be what? 0. So my result is, if I clean it up, 6x squared in front of the sine of 2x cubed. So the fundamental theorem allows you to work with bounds where one or both of them are variables. So that was your first intro to that. Let's try another one. Okay, so we're working on differentiating both sides, applying your rules of derivatives to one side and to the other. All right, so let's look at the function that's defined as y equals the integral of a to 2a. So both of these are variable bounds. Of the function 1 plus t squared, make sure you put parentheses around that, dt. And then we are being asked to differentiate both sides. So taking the derivative on both sides of that function. All right, fundamental theorem of calculus part 2, dy dx. Now, does anybody want to try it? They're gone. Okay, you don't have to be worried about it. Anybody want to try it? You're not changing anything about the function itself. The function itself is staying exactly the same. And you're not changing that. The definition of the fundamental theorem says when you've got an integral with those bounds, you keep the function. You have to do it. You don't have to do an antiderivative, and you don't have to do a derivative. It's just the function. But what do you plug into that? 2a goes in for the t position, so which is going to be 2a squared. And you have to remember, this is the thing that most often is forgotten, the chain rule. And what's the chain rule on 2a? 2. Okay, minus the function again, 1 over 1 plus, and this time I replace t with the lower bound, which is just a squared, times the chain rule on that, which is just 1. So my result is 2 over 1 plus 4a squared minus 1 over 1 plus a squared. And that's my derivative. You mean like getting a common denominator or something? Oh heavens. No, let's not do that. Okay, let's try another one. Y equals. Oh my goodness. Okay, hang on. Time out. I need to go back. I did not write this. This is dy dA because the variable is a. I had it right the first time, but I did not have it right that time. Okay, y equals 2x to 5. Which one's going to get plugged in first? Okay, just keeping that in mind. And 1 over t dt. Okay, differentiate both sides. Find the derivative. So dy d what is my variable? X. Okay, the variable is located in the bounds. Equals. Okay, who wants to try this one? Come on, you can do it. All right, Luke. 0. Good job. Okay, kept the function the same, plugged in the upper bound, and remembered his chain rule. Minus 2x. Okay, t is getting replaced with 2x, so there's no t anymore. Times what? 2. Okay, so the 0 wipes that term out, and I'm left with negative 2 over 2x, or negative 1 over x. Okay, new kind of example. All right, write a tangent line to the function y equals the integral of 2x to 5. It's the same function we just did. 1 over t dt. At the point x equals 1. All right, this is pulling together something that we did in first semester, writing a tangent line. In order to write a tangent line, you need to know the x-coordinate, you need to know the y-coordinate, and you need to know the slope. Those are the 3 things you need to know to write a tangent line. Well, we are given the x-coordinate to be 1. For the y-coordinate, well, we know what y is defined as. Y is defined as this. Okay, so my y-coordinate will be y equals the integral. What goes in for x? 1. So it will be the integral from 2 to 5 of 1 over t dt, which I actually have to figure out. Okay, that's not too bad. I can use my fundamental theorem of calculus part 1. Because I have both of my bounds, neither of them are variables. So the fundamental theorem says if they're not variables, then do your antiderivative, which is the natural log of x of t plus c, going from bounds 2 to 5, which will be the natural log of 5 plus c minus the natural log of 2 minus c. So I'm just skipping the plus c minus c part right now. There's my y, because both of the bounds were numbers. So I used fundamental theorem part 1. To do the slope, I need to find dy dx. To find dy dx, I use the fundamental theorem of calculus part 2. which means, was what I just did, what Luke just did for me, which is 1 over 5 times the chain rule of 5, which is 0, minus, I'm going back to the original bounds here, 1 over 2x times the chain rule of 2, which turned out to be negative 1 over x. Now I plug my x coordinate into that, which is negative 1 over 1, or negative 1. So now I have my x coordinate, my y coordinate, and my slope value. I have all three. And so I can write my tangent line. My tangent line is y minus y1 equals m times x minus x1. So it'll be y minus quantity, the natural log of 5 minus the natural log of 2, equals the slope of negative 1, and then x minus 1 as my x coordinate. That is your tangent line. You don't have to simplify that a lot. You could write the natural log of 5 halves if you like to write it as a fraction. That might, instead of 5 minus 2, we can use our natural log properties. And distribute your negative 1, that would give you negative x plus 1, but you don't have to do a ton of simplifying. You really can leave tangent lines in their original form. Okay, any questions about that one? So notice that the y coordinate was fundamental theorem. Maybe you want to label that in your notes, that was, we used part 1, because I plugged x in, and neither of the bounds were variables, they're both numbers. But the slope, I used part 2, and I didn't plug my 1 in until the end. That's the most dangerous thing about part 2 of the fundamental theorem. Well, there's two. One is people forget the chain rule, and 2 is they plug in their numbers too soon. Plug in your numbers at the end. Okay, last one. Okay, if the integral 5 to x, so as soon as you see that, you're like, oh, part 2 of the fundamental theorem is f of t dt. And if we know, we are given that that is equal to x squared plus sine 2x. Okay, if that is the given part of the equation, find f of x by itself. Okay, so if you are given the original equation, get f of x alone. Well, what do I have to get rid of? If I'm going to get the f function by itself, what do I need to get rid of? Okay, how do I get rid of that integral? What am I going to put in front of it? d dx. Okay, so I'm going to do d dx on both sides using the fundamental theorem. So d dx on this side, f of t dt, but I also have to do it on the other side. Don't forget, if you do it on one, you got to do it on the other. Okay, x squared plus sine 2x. On the left side, I keep f by itself. I plug in the upper bound of x, and I multiply it by the chain rule of 1. Minus f of 5 times the chain rule of that, which is 0. On the right side, I just take the derivative of each individual piece. So the derivative of x squared is 2x. The derivative of sine 2x is cos 2x times the chain rule on 2. The 0 wipes out the f of 5, and so f of x times 1 is 2x plus 2 cos 2x. If they ask me to find a specific value after that, I plug it in at this point. You plug it in at the end. So for example, if the question had said, find f of 7, you don't plug 7 in at the beginning. You find f of x first. And then you plug in f of 7 to get 14 plus 2 cos 14. So one of the dangers is plugging in a number too soon. Yeah?
If it would say instead of x like 2x, so it would be 2 f of x, and just 5 by 2.
Yes. Very good. Like it. Okay, good job. All right. So that is part 2 of the fundamental theorem, dealing with one or both bounds being variables in your problem and knowing how to use the rules of derivatives to apply to that.